So we're covering 4.4, 5, and 6. So I wanted to. I'm not gonna go like all of them. I'm just gonna go some of it, which I think is important and is worth to go through as well. So let's go with polynomial. So polynomial. So we always so we want to consider polynomial as vector space. That's how generalized vector space is. So previously, or we're gonna mostly deal with vectors in Rn. So vectors with n components or n, but we can generalize that. So we can axiomatize vector space, and then we can see all kinds of things, all kinds of interesting stuff are turning out to be vector space. So let's consider, so we got this fancy B. So we usually use fancy B to represent basis. So let's think of, what can I have the best example as possible. So let's go with 2 plus t. Or let's go with so let's erase this. So let's go with 1 plus 2t plus t squared. Now let's go with 1 plus t squared. And let's go with so in this case t might be a linearly dependent, so let's go with 1 plus t. Or let's go with to fancy it up, let's go with this one. I'm gonna go with t plus t squared. We got these three vectors. So is these three vectors basis 4. So let's write it as P2. So this is the set of all polynomials with degree less than or equal to 2. Question mark. So we got polynomial t plus t squared, 1 plus t squared, and 1 plus t. So the definition of linear independence is that any linear combination of this as zero vector, it only has 0 coefficients. So we have to solve c1 t plus t squared plus c2 1 plus t squared plus c3 1 plus t equals 0. So likewise as in Rn, so if we solve this and there's non-trivial solution, then in other ways it means that one vector is linear combination of the other two, which means that it literally means linear dependent. So linearly they're like dependent each other. But linear independence means that they cannot be made by other vectors. So fancy it up, we can go like solving this linear equations. If we always find that C1, C2, and C3 are all 0, then this is linear independent. So let's distribute C1, C2, and C3. C1t plus C1t squared plus C2 plus C2t squared plus C3 plus C3t equals 0. In this case, we always have the match of coefficients. We got constant term C2 and C3, C2 plus C3. We got t term C1t and C3t. So we put it as C1 plus C3 and t. And t squared term, we got C1t squared and C2t squared. So we got C1 plus C2t squared equals 0. So you got polynomial where left side is just 0. So this is not solving equation, but rather is just equating polynomials. So right hand side is not number 0, but it's a polynomial, like 0 polynomial. So that in order for us to match up, so in order for our left side to be equal as right side, all the coefficients should be 0. Now, so we know that knowing the linear independence of these three polynomial vectors boils down to solving system of linear equations C2 plus C3 equals 0, C1 plus C3 equals 0, and C1 plus C2 equals 0. So putting this into matrix equation, we got 0, 1, 1, 1, 0, 1, and 1, 1, 0. And you can put it or you can just ignore it, but we put the zeros on the right hand side. So what we do always is to row reduce. So we got a bottom. So let's put the bottom number to the top. So 1, 1, 0. And second row as it is. And first row to the third row. So we got a, let's say this one is first pivot. The first pivot, then eliminating all the bottom numbers. So eliminating this one here. So 1, 1, 0, 0, and 0, negative 1, 1, 0, and third row as it is. So now we got a second pivot here. Eliminating the bottom one, we get 1, 1, 0, 0, 0, negative 1, 1, 0, and 0, and this goes away. And 1 plus 1 equals 2, and 0. So here we see that, so 2C3 equals 0, so C3 equals 0. Here we got negative C2 plus C3 equals 0, where we know that C3 equals 0. So the C2 also is 0, and so on and so forth. So C1 plus C3 equals 0, so C1 also is 0. So we always get the case that all the coefficients are 0. Hence, so the set of vector B is linearly independent, so is a basis for P2. So we implicitly used the fact that P2 is dimension 3 vector space. This is spanned by this set of all polynomials with degree less than equal to 2. So of course this is spanned by 1 t squared. Dimension 3. We found 3 linearly independent vectors, so it is a basis. Or you can like call it as like a matrix inversion theorem revised, or you can use like a definition of dimension, and so on. So we got this basis here. Now the second question is, so the right, let's say, so what would be the best vector that I could possibly think of? So write 1 plus 4t plus 7t squared as a linear combination. Or let's go with so in other words, so it's basically the same thing. So write this polynomial as coordinate vector relative to b. So you want this vector, so this polynomial vector as linear combination of these three, and you want these three, and we want to write it as coordinate. So always solve C1 t plus t squared plus C2 1 plus t squared plus C3 1 plus t equals 1 plus 4t plus 7t squared. So we already match up coefficients here. This time, instead of all zeros, constant term should be 1 because there's 1. This should be 4 because t term has coefficient 4. And this should be 7 because t squared term has coefficient 7. So I'm gonna a little bit omit the detail, but basically this much, but the right hand side is just 1, 4, and 7. So this boils down to solving system linear equations, and you can put it into matrix form. 1, 4, 7. So basically, what we do is exactly the same as here. The only difference is that there are numbers on the right hand side. So changing third row, first row, 1107, 1014, 0111, and first pivot, eliminating bottom, 1107, and 0, and 1 minus 0. Oh, sorry, 0 minus 1 is -1. We got just 1. And 4 minus 7 is -3. And third row as it is. So we got a second pivot here, eliminating the bottom. We get 1107, 0, -1, 1, -3. 0, 0, and 1 plus 1 is 2. And -3 plus 1 is -2. So we can further, so we can go further to make it into reduced rational form. But you can go ahead and row echelon form as well and get the answer. So here we got 2 C3. Here we got 2 C3 equals -2. Divide by 2, you get C3 equals -1. And here we got negative C2 plus C3 equals -3. So C2, and plugging in, -1 equals -3. So you gotta put C2 to the right, -3 to the left. You got 2 equals C2. The last one, C1 plus C2 equals 7, where C2 is 2, so C1 equals 7 minus 2, so we get 5. So we got all these coefficients. So hence, explicitly writing this polynomial, then it's going to be 5 t plus t squared plus 2, 1 plus t squared plus, in this case, the negative, so it's going to be minus 1 plus t. So that, so in other words, coordinate vector of this polynomial vector, so this is 5, 2, and -1. Basically, so all the methods are straightforward, easy. What I would worry a little bit is that, so after seeing these vectors, some students are gonna just align vectors like this. But so let's say this number was 2. Here's 2, so that this is 2, this is 2, so that this is 2, so that yeah, let's go with this. This is 2. It's not this one and this goes here, so that it's not that 0, 1, 1. This one goes in vertical line. So instead of here, it goes here. This one, it goes here. This one, it goes here. So I want you to a little bit careful about this when dealing with polynomials. It's, so 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 other so other than like so 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 different from other like Rn cases, it goes like vertical. Okay, so any questions? Okay, then let's go to change of coordinate. So let's consider two bases in R2. So let's say B equals 1, 0, 1, 1, and C is, let's say, like 1, 2, and 2, 1. So these two definitely are bases. It's not our main concern, but these two are definitely bases. But so can anyone tell me why these two are bases for R2? So what kind of method can we use here? Someone?
I'm sorry, what was the question?
So the question is, considering these two set of vectors, what method can we use to know that um, these two are all bases for R2?
Um, is it if they're linearly independent?
If these two are linearly independent,
Yeah.
definitely it's going to be bases by matrix inversion theorem. So if instead of n many vectors in Rn, if it is, so it has various forms. Like for one, like row echelon form doesn't have 0 rows, and all the good stuff happens, like a linear independent span, and like a CNS linear transformation is onto n 1-to-1, and determinant is non-zero and so on. But yeah, so basically we have to use matrix inversion theorem in particular. So you can just use row reduction. You can use yeah, like the one that's simple enough is just like using row reduction. But so I'll go row reduction. And so indeed, the 1011 it's in already um, row echelon form, right? With all surviving pivots, no 0 rows. So by matrix inversion theorem, we don't need to invoke matrix inversion theorem, but so if all the so there's no 0 rows and all the good stuff happens. And so what about C? We can also use row reduction and make it into row echelon form, see if there's no 0 rows. But this time I want to use determinant. I want to calculate determinant of matrix made um, by columns being these two vectors. This is 1 times 1 minus 2 times 2. So 2 by 2 matrix is, so it follows 80 minus B0, -3, non-zero. So by matrix inversion theorem, he also is basis. It's kind of yeah, just a side note. Then what we want to get is change of coordinate vector from B. I'm sorry, from C to B. So what else? So what could this be? Now, so let's think about this. So let's get this mental picture here. We got R2. I'm gonna draw as like a diagram. R2 as well. We're, we're going to have like this vector. So let's say vector. Yeah, just go with X. Vector X, but it should have coordinate vector relative to C because C is a basis. So it's going to have like one and only unique linear combination to make X, so we can make it into coordinate. Let's let's just put this as C1, C2. And sending this, we're going to get coordinate vector with respect to B in this time. So let's go with B1 and B2 like this. So so we know, so we took coordinate vector relative to C and B as C1, C2, and B1, B2, so we know what X is. So X is C1 times, let's go with first vector 1, 2, plus C2, 2, 1. And here, same X also can be represented as B1 times 1, 0, plus B2 times 1, 1. So basically what we're doing is to solve C1, 1, 2, plus C2, 2, 1 equals B1, 1, 0, plus B2, 1, 1. Where the left hand side is 1, 2, 2, 1, and C1, C2. And this side also can be written as 1011 and B1, B2. But notice that so so let let's so let's so let's put it in this way instead of this. So so representing in this way, and just taking inverse of matrix is going to give you answer. It's basically same method, but I want to use row reduction. So this means that C1 plus 2C2 equals B1 plus B2, and 2C1 plus C2 equals B2. So it boils down to solving system linear equations of this form. Let's write it in matrix form. 1, 2, 2, 1, and we got just a dotted line to distinguish 1, 1, 0, and 1. So let's solve this. So first pivot, eliminate the bottom. So first row, and we're gonna multiply first row by -2 and add the second row to eliminate this 2. So this becomes 0. And 1 minus 2 times 2 is 1 minus 3 is, I'm sorry, 1 minus 4 is 3. We got 0 minus 2 times 1 is -2. And 0 minus 2 times 1 is, I'm sorry, 1 minus 2 times 1 is 1 minus 2 is -1. So we got this a -3 here, so I want to divide second row by -3 to make this into 1. So 1, 2, 0, 1. Got 1. So first row is 0, 1, and 2 over 3, and 1 over 3. Now we want to eliminate this 2 here. So we want to multiply second row by -2 and add to first row. Second row as it is. 1 and 2 goes away. 1 minus 2 times 2 over 3 is 1 minus 4 over 3, which is -1 over 3. 1 minus 2 times 1 over 3 is 1 minus 2 over 3, so it's that 1 over 3. So what we did is that, hold on a minute. So we want, oh yeah, so we want C to B, right? C to B. Yeah, then so let's make this identity. This is gonna be way easier. Erase this. So make right hand side identity matrix. So here is so right hand side is very easy, right? All we have to do is eliminate this one here. And second row as it is. But subtract the first row, then 1 minus 2, -1, 2 minus 1 is 1, 1 minus 0 is 1, and it's 0. So this means that -C1 plus C2, I'm going to erase this to avoid confusion. All right, there we go. -C1 plus C2 equals B1, and 2C1 plus C2 equals B2. So not, yeah, in other words, so -1, 1, 2, 1, plugging in C1, C2, which is the coordinate vector relative to C, is B1, B2, which is a coordinate vector of X relative to B. So C, sending, and B. So this is what we're looking for. So nothing, so nothing to memorize, right? So in some sense, you're gonna be confused. Is this like, so if I have to reduce it, I have to make this as identity or this as identity, or if I have to put like vectors here or here. If you follow up basic steps, and so follow up like this basic algorithm, then you're gonna get like a answer regularly. So basically all the all the like crash courses, all the small lectures that I do, you can see that I don't memorize anything. It's just like straight up just doing calculation. Maybe this one, matrix inversion theorem. It all so it all has like some basic like explanations that you're gonna like follow the flow and get the answer. Okay. So any questions so far? Then let's go to eigenvector and eigenspace, eigenvalue, and diagonalizable. So, that's what square matrix A we got square matrix multiplied by vector spits out lambda multiple of itself. We call this lambda as eigenvalue. This x as an eigenvector. So many of the students have asked in quiz that -1, -1, and 1, 1. So both are eigenvectors. In fact, there are infinitely many in eigenspace, except for 0 vector. So eigenvector rule is that eigenvector never becomes 0 vector. So just to emphasize, I'm just going to make it into a boldface 0. So to emphasize, it's not 0 vector. So as name suggests, so eigen is a cognate of own. This is kind of is literally is a own value of matrix. Kind of has it. Let's see. So let's look at some example. So let's consider A equals 1, 1. Yeah, let's go with 1, 1, 0, 1, 1, 0, and 0, 0, 1. Yeah, let's go with this one. Just gonna change the system. So what we have to do first is to make characteristic equation. If it's triangular matrix, then it's just like it's just a giveaway. If it's triangular matrix, upper or lower, all you have to do is just pick up main diagonal entries. That's going to be those are going to be your eigen values. In this case, it's not triangular matrix. It has values. So we have to calculate characteristic equation. So characteristic polynomial is defined as the determinant of a minus I. I'm sorry, a minus lambda I. I is in this case 3 by 3 matrix, so it's identity matrix. So in order for us to subtract lambda I, all we have to do is subtract on main diagonal entries. So 1 minus lambda and 1 O as it is, 1 O as it is, but 1 minus lambda, O as it is, plus 2 minus lambda. So always, if you want to, so in this case, I'm going to use a cofactor expansion for finding determinant. Always, when you want to expand, then 0 is your friend. You got 2 zeros here, 2 zeros here, so you can expand in here. You can cofactor expand in here. I'm just going to choose this one. We got 2 friends, so let's expand it. Let's specify signs. So our sign matrix is plus, minus, plus, minus, plus, minus, plus, minus, plus. It signifies the signs of cofactor expansion. We're starting from here. It's going to go with signs as plus, minus, plus. So 0, 1, 0, 1 minus lambda 0. It basically goes away. I'm just going to write it for better understanding. For you. So minus 0 and this much, and plus our coefficient is 2 minus lambda, and this much. 1 minus lambda, 1, 1, 1 minus lambda. Of course, 2 with 0 coefficient all goes away. We got 2 minus lambda. 2 by 2 matrix, determinant is 8, follows 80 minus BC rule, so 1 minus lambda squared minus 1. So we got 2 minus lambda, and we got lambda squared minus 2 lambda plus 1 minus 1. This goes away. So we got lambda 2 minus, so we got 2 minus lambda, and lambda minus 2. Fancy it up, taking a negative sign out, negative lambda, and lambda minus 2 squared. This should be 0. So our um, eigenvalues are so 1 lambda, 2 lambda minus 2. So considering multiplicities, we can conclude that eigenvalues are 0, 2, and 2. So let's go with lambda equals 0 case first. You can go with 2 case first or 0 case first. I'm just gonna go lambda equals 0 case. Then our eigenspace, this is null of a minus lambda I. Basically, is all the x such that this holds, right? This definition holds. We want to collect all those eigenvectors and call it as eigenspace. A little bit different is that since it is vector space, we're adding 0, but eigenvector never can be 0. Just a little bit detail. But anyway, so let's calculate this eigenspace with lambda equals 0. So lambda equals 0. So this is just the null space of A. So let's write it this way. So null space by definition is a set of vectors such that multiplied by A gives us 0 vector. So it boils down to solving system linear equations, non-homogeneous one, because right hand side is 0. So row reducing it, we get so 1, 1, 0, 1, 1, 0, 0, 0, 1, now 0, 2. So first pivot, eliminating the bottom, 1, 1, 0, 0, 0, 0, 0, 0, 2. It's just going to be 1, 1, 0, 0, 0, 1. So pulling up and divide by 2, and 0 on the bottom. So this becomes, so our eigenspace becomes that of all x, y, z, such that multiply this by vector gives us 0 vector. So I'm just gonna just to avoid like redundancy, I'm just gonna write it as x plus y equals 0 because x plus y equals 0. This one as well, all zeros, but c survives and it's gonna be equal to 0. And third row is just the bottom rows, it goes away. So x here equals negative y. So this becomes, so x equals negative y as it is, and z equals 0, where y just varies. Our negative y 0 is y multiple of negative 1, 1, 0. So basically, the set is all the multiples of negative 1, 1, 0. Basically, it is span of negative 1, 1, 0. We got our eigenspace here. So let's go with lambda equals 2 case. It's 2 case. It's 2. Our eigenspace is null space of a minus lambda I. In this case, lambda equals 2, so a minus 2i. So that, so what was our a? So it was like 1, 1, 1, 1, and 2. So it's a null space. So got 1, 1, 1, 1, and 2. This kind of convention that if I omit entries, then those are all zeros. It's just like trivial. And we divide by, subtract by 2i. So we subtract negative 2 on main diagonal entries. So this becomes null space of negative 1, 1, 1, negative 1. This goes away. I'm just going to go row reduction. So first pivot, eliminating, boom. It's basically null space of negative 1, 1, all zeros. It's just really trivial. So this is set of all x, y, z, such that negative x plus y equals 0. All the others, just like zeros, just goes away. I'm just omitting a little bit calculations and like formalities, just like avoid redundancies, calculating all that. So negative x plus y equals 0, so x equals y. So this is set of all y, y, z, where y, z just varies. So this is, so taking y out, 1, 1, 0, taking z out, 0, 0, 1. So this actually is span of 1, 1, 0. So this set is basically a linear combination of 1, 1, 0, 0, 0, 1. By definition, it's just the span zeros, 1, 1, 0, and 0, 0, 1. Okay. We got eigenspace here. Now this is very important. Is this matrix diagonalizable or not diagonalizable? It's very important. Is it diagonalizable or not? No one?
Did you ask if it was diagonalizable?
So you think it is diagonalizable or?
Uh, no, because it's not like an n by n matrix.
Okay. So anyone thinks it is diagonalizable? Or anyone thinks like it's just not diagonalizable?
I'm sorry, I just got back from getting something to drink. What are we talking about? Which matrix?
So looking at this eigenspace,
Yes.
is this matrix diagonalizable or not diagonalizable?
If I remember correctly, in order for it to be diagonalizable, or however you pronounce it, doesn't it have to be an NXN or NXN matrix? If that's correct, I think so. And that isn't, it's a 3x2.
And xn. Um, um, and xn.
Yeah, like
So
it
the-
has to be like a square. Sorry, it has to be a square matrix, not a. If that helps.
Um, so if you so if you elucidate a little bit, then I guess we're gonna like get like answer. But so I wanted to be like a little bit to elucidate like if you had like something that it's gonna be correct answer. But so so we got so let's count all the linearly independent eigenvectors. So I'm not counting all eigenvectors. I'm just counting number of linearly independent eigenvectors mutually. So lambda equals 0 case, at all these, boom, and negative 1, 1, 0. We got one linear independent eigenvector. Lambda equals 2 case, where 2 had multiplicity 2. So we had um, two eigenvalues with 2. And we got 2 linearly independent eigenvectors. It's a total of 3 linearly independent eigenvectors. Is this diagonalizable or not diagonalizable? So we got three vectors, or 3, so yeah, it becomes like, so or you can think of it as like square matrix. But
Wait, saying that if they're all linearly dependent, they're diagonalizable.
they're diagonalizable. Okay. You think it's well then so we got 3, but what happens if it's 2? Is it diagonalizable or not diagonalizable?
with a span of two matrices, wouldn't it be not diagonalizable?
But that's correct.
Okay.
In order for us to be diagonalizable, we have to have, in this case 3 by 3, we should have 3 linearly independent eigenvectors. this case, we got lucky, so we got all threes. In other cases, you know, a little bit deeper, lambda equals 1 case, you must have eigenspace, or linear, at least one linear independent eigenvector. Lambda equals 2 case. So it has at least one, but since we have two, it's diagonalizable. So we call that as diagonalization theorem, or so like name like that in the textbook. Very important. So our conclusion is that since we have three linearly independent eigenvectors, A is diagonalizable. Very important. If it's diagonalizable, we have to diagonalize it. So A can be represented as PDP inverse. 3 by 3, 3 by 3, 3 by 3. Put inverse for the last one. Let's go with lambda equals 1 case. I'm sorry, lambda equals 0 case. We got eigenvector -1, 1, 0. So all we do is just align all these vectors. It was -1, 1, 0. We got 0 eigenvalue, -1, 1, 0. Lambda equals 2 case. We had notice that we had multiplicity 2. We have two vectors, 1, 1, 0 and 0, 0, 1. 1, 1, 0, 0, 0, 1, corresponding 2 and 2, 1, 1, 0, and 0, 0, 1. So this is our, so if I omit all these, it means that these are all zeros. It's just all trivial. This is our eigenvalue. Sorry, diagonalizable form. So let's go with another example. Let's call it a day. Everyone's following it? Everyone's following that why this is diagonalizable? Everyone's cool?
Yeah.
Okay. Now, for the last example, let's go with something that's not diagonalizable. Let's go with A equals 1, 1, 1, 0, 1, 1, 0, 0, 1. Now, this matrix is triangular matrix. And so in particular, upper triangular matrix, because all the bottom numbers are dead, like all 0. Then if it's triangular matrix, eigenvalues are taken for granted as main diagonal elements. So we got 3 lambda equals 1s. So all we have to do is calculate eigenspace for lambda equals 1. Then null space of A minus, in this case, lambda equals 1, so A minus I says null space. So subtracting 1 to all the main diagonal entries, we get 0, 0, 0, and 1, 1, 1. All zeros. Already and row echelon form, all we have to do is eliminate this upper number at this one by row reduction, then boom, then we got 1, 1. This is set of all x, y, z, such that in this case is y equals 0. In this case here, z equals 0, and the row just 0. Plugging in y equals 0, z equals 0, we get x 0, 0. X is arbitrary number, and x is, when you take it out, this vector is x multiple of 1, 0, 0. So this is span of 1, 0, 0. Very important. Is this matrix diagonalizable or not diagonalizable?
It's not diagonalizable
Okay, so why is it not diagonalizable?
because there's only one linearly independent vector to be used for P.
Right, that's excellent, excellent. That's right. You only have one linearly independent eigenvector since there's only one linearly independent eigenvector A is not diagonalized. So always count number of linear independent vectors. Yes, and you can also think of it as like there's not enough vectors to put inside P. This another good explanation or ways to think about it. Not diagonalizable. And yeah, so it's so all the methods, like I said, calculate. So we have a lot of things to write, right? As notation, or even in the exam. This course is actually this is kind of course that so it's not conventional course, right? It's asynchronous online class. Almost 60 students. There's like a 55. After exam is done on like a lockdown browser and all that. So that it is unconventional. So one thing that and all the modules are already built in. They let you follow all the course. One thing that I put a little bit this is something that I would think that I wanted to do was to see students like write stuff, write all the stuff in exam. So I'm actually doing for homework, so I'm putting more time on grading homework. But, yeah, so
Do you have time to go over a question from the review?
we have 8:58.
Yeah.
So yeah, or yeah, sure. Or
Right.
if y'all wanna go, then you can. Anyone who wants to leave, you can leave. Yeah, leave. So okay, so do you have any question on the review?
Yeah, I just was confused on question 13 of the test 3 review.
Question number 15. So we got so this one's not we're not gonna include this one, yeah.
Oh, okay.
So this difference method, so we haven't covered this, so
Okay. And number 12 on finding the x and the vector x for C, specifically that last part.
so let's go with this one. The camera. So we got two bases, B and C, so we got B equals B1, B2, C, C1, C2. And the conditions are given as B1 equals C1 minus 6, C2, and B2 equals 4, C1 minus 3, C2. So find the change of coordinate matrix from B to C. So let's think about this. So as always, we gotta, well, technically, so technically it's like a vector space. So they claim that it's just a vector space, which can be polynomial space or R2. It doesn't have to be, it doesn't have to be R2. Like B1, B2 doesn't have to be vectors in R2, but we know that dimension of V at least is 2 because we got two bases with 2 elements. So dimension of V is 2. Let's think about B going to B. We had a so let's take the arbitrary vector in X and represent it as like B here represented as C. extending this by using change of coordinate matrix from B to C. So matrix and linear transformation, those two are basically identical. Meaning, so this is, let's say this is B1, B2. So without boldface, this one, C1, C2. Then our C1, C2. So X is C1 boldface C1 plus C2 boldface C2, just by definition, right? Let's go from this one. Its conditions are given as B1 equals and B2 equals. So X is B1 boldface B1 plus B2 boldface B2. So let's plug these two in. C1 minus 6C2 plus B2, 4C1 minus 3C2. So this is B1 plus 4B2 C1 plus negative 6B1 minus 3B2 C2. So our change of coordinate matrix, C, this is B1 plus 4B2, negative 6B1 minus 3B2. This should be equal to C1 and C2. And notice that the left-hand side can also write it as 1, 4, negative 6, negative 3, and B1 and B2. So B1, B2, coordinate vector multiplied by this matrix spits out C1, C2. So this is our change of coordinate matrix from B to C. Now, C to B is just simple, take the inverse. So P, C to B this is B to C, taking inverse. So inverse of 2 by 2 matrix, it is, the formula is given as 1 over AD minus BC, and switch D and A, put negative signs on B and C. So 1 over negative 3 plus 24. Here's our negative 3, 1, negative 4, and 6. So this is our 1 over 21, and negative 3, negative 4, 6, 1. And the last question is, suppose x equals b1 plus 3b2. So in other words, coordinate vector of x relative to b is 1, 3. So in order for us to coordinate vector of x relative to c, all we have to do is use this matrix. So coordinate vector of x relative to c, this is this matrix multiplied by 1, 3. The horizontal line, we got 1 plus 12, negative 6 minus 9. We got 13 and negative 15. Did that help you, or?
Yeah, but the question also asks that you find x.
Find x?
Yeah, it says find x and xc, but I understand how to do the second part. Just find x doesn't make sense to me.
I guess it's just a typo. I'll just delete it.
Well, question 11 asks the same thing too, so I was just.
Yeah, I think it's just typo. Yeah,
Okay.
I'll just fix it.
Okay.
All right. Any questions?
Yeah, so on the review, you said that 13 wasn't something that we talked about. Is there anything else on the review that's like that? Or is it just 13? Like, are there any ones that we should like not even focus about? Like other questions on the exam review?
16, 17, and 18 are the same as 13, like the same kind of question.
Yeah, you have to exclude all these 16, 17.
Okay,
13.
cool. Okay, thank you. Because I was doing them earlier and I was like, man, I don't remember doing this in the
Yeah.
book. So I was
I-
like, I guess I must have missed it. I guess. But thank
yeah.
you, I appreciate it.
Yeah, no, I mean like, yeah, it's like 10 weeks, so like, I'm just like, we had to skip like some applications, a little bit intense. So yeah, like yeah, let's skip out 13, 16 to 18. Any other
Um,
questions?
Yeah, I have two small questions. For question 14, I understand the characteristic equation, but I was wondering, are they always going to be in coordinates? Like, well, not coordinates, parentheses like that? Or will any of the answers ever be expanded out? Or does it just depend?
Parentheses like matrix or
Um, like the answer that's for 14, for question 14, will it always be in that format or will it or could
let's check.
it expand?
Um, um, I wouldn't if the question asks just characteristic equation, you don't have to like factor out like this. But
Okay.
or nor do you have to like expand it.
Okay.
Both are fine. Like either you expand it or factor it out. Those are fine.
Okay. And I also have a question about 15.
Okay.
Like find the characteristic equations and the eigenvalues of the given matrix.
Hmm.
Like the answer was just 2, 6.
3,6. This one. Hmm. Yeah, I guess like this one's like like as well. Yeah, I'll fix this one as well.
Okay.
Okay, thank you so much. Yeah, that's a lot of like typos here. It's watching. Any other questions? Okay, so if you have no questions, I hope this finds helpful. Some review course, all the crash courses. And, I hope you have best result on the exam.
Great. I have one more question. I'm so sorry.
Yeah,
But
sure.
for 14, I noticed that 14 is a triangular matrix. I hope I'm not wrong. Like
So
for
it
the
has, so it has like, so in order for this to be triangular matrix, in particular upper triangular matrix, you have to have all the bottom numbers 0. So you have like 3 and 6 surviving. So it's not triangular.
okay. Okay, that was what I was gonna ask about the characteristic equation. Okay. Thank you. So it doesn't have to be a triangular matrix. We just take the diagonal.
It doesn't have to be triangular matrix, but if it is triangular matrix, then it's like a giveaway. Like you can just like take all the diagonal entries, but if it's not triangular matrix, then you have to find the characteristic equation and solve it.
Okay. Okay. Thank you.
Okay, then that's for today, and I hope you have a great result, and I'll see you probably on Friday.
Have a good day.
You too.